Axel, when you get a chance, will you go ahead and start your screen share? And Omer, you could mute yourself, or should I mute you? Welcome everyone to the second talk of this session. We're very happy to introduce Axel Hultman. He's going to be speaking on shortest paths, inversion, arrangements, and the weak order. Take it away, Axel.
Thank you, Sarah. And down here in red, you can see the URL for these slides. So, by the way, can you hear me? Because I don't see myself in the active speaker window.
Yes, we can hear you, Axel.
Excellent. So let's take it away. So this takes place in a finite reflection group, capital W, or if you like, a finite Coxeter group. And the set of reflections in there will denote by T. So these are orthogonal reflections in some real space. And if you choose an element in this group, lowercase w, reflection is an inversion if when you multiply by this reflection from the right, you go down in Coxeter length. So inversions today will be right inversions. That's for convenience. And all the reflections correspond to the positive roots once we have chosen the root system and the choice of positive roots. And the reflecting hyperplane is sort of the orthogonal complement of the corresponding root. So if you then take all the reflecting hyperplanes that correspond to the inversions of our chosen element, we get what is known as the inversion arrangement. And I will denote this by this curly A subscript W. So it's a central hyperplane arrangement in real space, and we can do this standard construction constructing the intersection lattice. So you take all possible subsets of hyperplanes in your arrangement, and you take the intersections that you get. So those will be a bunch of subspaces, and you can order them by reverse inclusion. And it happens that this becomes a geometric lattice, so it's the lattice of flats of the corresponding matroid. Either you might think of the matroid as coming from the hyperplane arrangement, or maybe from just the arrangement of roots, if you like, corresponding to the inversions. So here's an example. This will be the running example throughout this talk. So let's pick type A, where we have a symmetric group, S4 in this case. We choose an element pi. In one-line notation, it's 4, 2, 3, 1. And the inversions, since I've chosen to make inversions right inversions, will be the transpositions that flip to positions where the entries in those positions are placed in the wrong order, so the biggest first. So in this particular element 4, 2, 3, 1, all of the reflections, all of the transpositions will be inversions except one. It's the 2, 3, because those letters come in the correct order, so that's not an inversion. All the other 5 are inversions. And the corresponding hyperplane arrangement consists of the fixed point spaces of these transpositions in the natural reflection representation. So the equations for these are these 5 equations. So for example, the transposition 3, 4 corresponds to the hyperplane with the equation x3 equals x4 in R4, say. And if you construct the intersection lattice, take all possible intersections of these 5 hyperplanes, you get this thing. So I have labeled the elements using set partitions of the 4-element set. And the correspondence with the corresponding subspaces is that in a partition, for example, this one, The elements which are in the same part or in the same block of the partition, 2, 3, 4 in this case, indicate that those coordinates are the same in this subspace. So the subspace corresponding to this partition has equations x2 equals x3 equals x4. And this is the full intersection lattice. And we'll come back to this example later on. So at the bottom here, you don't have any equations. So it's the entire ambient space. And at the top, you have the intersection of all the hyperplanes where all the coordinates are equal. So there's a different family of objects that you can associate with W. So first of all, let's define the Bruhat graph of the entire group. So it's just a Cayley graph, essentially, if you choose the reflections as your generating set. So the vertex set is the group itself, and you get edges between vertices if you go from one to the other by multiplication using a reflection. And we direct these edges according to, well, Coxeter length. So the edge points towards the element which is the longest. And sometimes I will want to associate a particular reflection to an edge. And then it's good to remember that our multiplication is from the right by convention in this case. So this is a directed graph. You can take the transitive closure, you get the partial order, and this is called the Bruhat order on W. And I'm interested in subsets of this Bruhat order, subsets generated by an element. So you take the principal order ideal generated by your fixed element W. And since the Bruhat order has a unique minimum, the identity element, this principal order ideal is an interval, a lower interval from the identity to W. And if you only take those vertices, those group elements which are in this interval, they induce a subgraph of the Bruhat graph. And this I will denote by B of W. And I will call also that a Bruhat graph. And note that now when I construct this B of W, I forget about the directions. So I don't want this B of W to be directed. So it's an undirected graph. And here is an example. So we are starting with the same W as before, this permutation 4231. And you can construct the Bruhat graph, all the elements below this permutation in Bruhat order. And you add in all the edges coming from multiplication by reflections. So there's lots of edges there. And you can notice that most of them are short edges. And some of them are a bit longer. And if you look carefully at these long whirly edges, there are 7 of them. If you remove those long edges, you are left with a Hasse diagram of this Bruhat interval. So that's also contained in this picture. And it's worth noting, we'll use it a little bit later, that it's an old result by Dyer if you only know the abstract poset of the Bruhat interval, so only the incidences, not the labels, then you can reconstruct the Bruhat graph. So you can reconstruct the long edges from the short ones. So that information is already contained in the short ones. And here is a connection between these two pictures, the arrangements on the one hand and these Bruhat intervals of Bruhat graphs on the other hand. So this is a connection which was conjectured by Alex Postnikov in 2007, and it came out of work which was sort of related to what Lauren was talking about yesterday, the cell decompositions of the totally non-negative Grassmannian. And together with Svante and John and Jonas Sjöstrand, we proved this conjecture. And so here is the statement connecting them. I will tell you about this NBC thing in a bit, but there is an injective map from the set of NBC elements, so no broken circuit sets, into the Bruhat interval. So what is this NBC? I will not define it, but it's something that you can associate with any matroid. So the NBC sets are certain distinguished bases of the flats. And once you have these distinguished bases, there are all kinds of nice properties. For example, the number of NBC sets is the same as the number of chambers in the hyperplane arrangement. So that's where this corollary comes from, and that was the reason we were interested in this, that since the number of NBC sets is the same as the number of chambers, you get this inequality from this injective map. So the number of chambers of the arrangement is at most the number of elements in this Bruhat interval. And there are more interesting correspondences. For example, if you count the NBC sets by cardinality, so you only take the ones which are of a certain fixed cardinality k, then that number is a corresponding Betti number of the complement of the complexified inversion arrangement. So these NBC sets give you all kinds of Betti numbers on the arrangement side. And on the other hand, this interval provides you with some Betti numbers on the Schubert variety side. So if you're in a Weyl group, if W is a Weyl group, then lowercase w corresponds to a Schubert variety. And when you decompose that variety into cells, you get one cell for each element in this interval. And if you actually count them by rank, you get the Betti numbers of this variety. So there's all kinds of geometry lurking behind this connection here. And this is why we are interested in this. A couple of remarks. You might wonder what happens when you actually have equality here. This was conjectured by Postnikov in type A, and we proved that you can characterize this using permutation pattern avoidance. The permutations that avoid certain patterns are precisely the ones that get equality here. And you can make a very long story about these permutations. They appear all over the literature, but let's not make that story that long right now. In type B, there's a recent characterization, also in terms of pattern avoidance, but in terms of so-called Bialy-Postnikov patterns in reflection groups, due to Alex Wu. Very nice result. In general, you can characterize equality in terms of the Bruhat graph, looking at certain paths. I will get back to things that have to do with this later on. Let me also mention this result, a very nice result due to Sjöstrand. Equality in this inequality, together with the arrangement being free, so free in the sense of terao, that a certain module of derivations is free. If you have those two things, equality and freeness, then that's actually equivalent to the Schubert variety being rationally smooth. And in fact, I didn't state it here, but in that case, you can say much more. You can relate these Betti numbers that I was talking about on the one hand on the arrangement side, and on the other on the Schubert variety side. And there are nice factorizations there which are related. So that's also a result of Sjöstrand. In type A, it was proven already by O. Postnikov and Yu. So there are all kinds of connections here. And what we are really interested in here is to understand how this connection between the arrangements and the Schubert varieties, I mean, what is happening, what kind of information is transferred between these two settings, what kind of information is lost, and what does this map phi have to do with this. So that's the upshot for what is coming here. So the point here is that I want to describe what kind of information on the arrangement side only depends on the poset structure and not on the particular labels in the Bruhat order. So this is where this is leading. But here, let's start all over. Pick any graph G, connected, simple, and undirected. And you take a distinguished vertex, V0. So we'll start walking from V0 to the other vertices. And let n of v0 be the set of neighbors of v0. So when we start walking from v0 to the other vertices, we will pass through these neighbors. And for each vertex in the graph, let f of v be the set of neighbors that you pass through if you take some shortest path from v0 to v. So f of v, I will call it a quick step set. So it consists of those neighbors that you may visit if you want to go as fast as possible from v0 to v. So it's some subset of the neighborhood, of the neighbors. And you can order all of them. If you take this quick step set for every vertex, you get a bunch of sets of neighbors. You can order them by inclusion. You get this quick step poset, which depends on G and on the starting vertex. So of course, now we'll apply this to Bruhat graphs. So here is the Bruhat graph again with this example element 4231. And we want to describe this quick step poset with starting vertex, the top one. So remember, the idea here was that we want to understand what kind of information we get ignoring the labels and only remembering the incidence structure of this graph. So let's remove the labels. And then we play this quick step poset game. So the starting vertex is the top one. That means that its neighbors are important. It has 5 neighbors, A, B, C, D, and E. So the quick step sets will be subsets of these 5 elements. So there is one for each vertex in the graph. So what about the top vertex? Well, the fastest path from the top vertex to itself doesn't use any steps. So it never visits a neighbor, and therefore the quick step set is empty. Let's look at this vertex down here, this one. If you want to go as fast as possible from the top to it, you might see in the graph that you can do it in 2 steps. There's actually only one path that works with 2 steps. You start at the top, you go all the way to the bottom, and then you go here. That's the only shortest path. So it must visit this neighbor C, and therefore the label is the singleton C. Let's do some more examples. So let's look at this vertex. The shortest path from the top to it has 2 steps, but now it's not unique. There are different such. For example, here's one 2-step path which visits D, and there's another which visits E. So the label becomes DE. And finally, let's do a final example. Let's take this vertex. Well, if you inspect the graph, you see that the shortest path from the top has 3 steps. And if you inspect it a little bit more, you will see that actually you can visit any neighbor in a 3-step path. So for example, you can visit A by walking in 3 steps from the top like this. First you go to A in the first step, in the second step you go down here, and in the third step you get to this vertex. So you can walk through all of the neighbors, so you get the full set of neighbors as your quick step set. And you play this game with all the vertices, and these are the sets that you get. You collect the sets that you have. Here is the list, and you order them by inclusion. So this is the quick step poset corresponding to this particular graph. And of course, you may recognize this poset. If I change the labels to some partitions, then this is the example we had before. So this is the lattice of flats, of the corresponding permutation that we started with. So, and of course, this is not a coincidence. This is a theorem. Whichever vertex you start with, the corresponding lattice of flats, the intersection lattice of the inversion arrangement, is the quick step poset of the Bruhat graph with starting vertex W. And the reason we started thinking about this was partly because of this old question of ours. We asked whether or not the inversion arrangement, or the matroid, is a combinatorial invariant. In other words, does the abstract pose set, the Bruhat interval, determine the isomorphism class of the intersection lattice? And this shows that it does, because, as you remember, the pose set determines the Bruhat graph. That was the result of Dyer. And the Bruhat graph, as we just saw, determines the intersection lattice. So as a corollary, yes. Okay, so let's look at some application of this actual construction of the intersection lattice. So this is the connection with the weak order, which was in the title. So the weak order, there are actually two of them, a left weak order and a right weak order on W. But we will choose the left weak order because we have chosen the right inversions. And one way to define the left weak order is by inclusion of right inversion sets. And this is a sub-poset of the Bruhat order. So it's a weaker order than the Bruhat order, as you can tell by the name. And in a recent paper by Fan, he connected, in type A, he connected the weak order with these inversion arrangements. So for all permutations in a symmetric group Sn, you look at the principal order ideal, so the interval from the identity to your element in the left weak order. And then this number of elements is at most the number of chambers of the inversion arrangement. So notice that this inequality goes on the opposite direction compared to how it was in the Bruhat order case. In the Bruhat order case, the interval is bigger than the number of chambers. Here it is smaller. And he was also able to characterize equality. It holds if and only if this permutation avoids these two simple patterns. And actually there is a nice explanation for why these particular patterns appear, which you will see in about 10 seconds. So of course, he conjectured that this inequality holds in all types. And if you make a scrutiny of the construction that I showed you of the quickstep pose set, actually it's a very technical scrutiny. I will not at all show it to you, but it's elementary but tedious. You can deduce this theorem that this inequality actually holds the way you conjecture. So these numbers are related in this way. Of course, this last inequality is the one with the Bruhat order that was known before. Actually, more is true. I didn't write this on the slide, but if you think about this map phi, this injective map from the MBC sets to the Bruhat interval, well, the cardinality of the MBC sets is the same as the number of chambers. So that means that the image of this map has this cardinality. It's the number of chambers. So this is the cardinality of the image of phi. And in fact, what we can prove is that this interval, this weak order interval, is always in the image of phi. So remember that the construction of phi depends on an order, a choice of convex order of the reflections, of the inversions. In other words, it's a choice of reduced expression for the element W. So the construction of phi depends on this choice, and the image depends on this choice. But in all situations, no matter how you do this choice, the weak order interval will be in the image. And we can also characterize when we have equality. This will be strict unless W is the longest element of a standard parabolic subgroup. And if it is, then all these numbers are equal. And in fact, the underlying sets are also equal in that case. So that's actually where these two patterns come from, if you think about it. They characterize being the longest element of a standard parabolic subgroup. Okay, let's look some more on this map, this phi. So we already, on the previous slide, saw some characterization of the image of phi. I told you that it always contains this weak order interval. But maybe you can say more about this image. So we have this map from the MBC sets to this into this Bruhat interval. What can we say about the image? Well, here are some technical statements. Let me just, you can read them and digest them if you want to, but let me just tell you what they really say. And there's a picture on the next slide that will make it clearer. So if we have an MBC set, let's call it B, then it generates a flat in the intersection lattice. Well, a flat in the intersection lattice is the same as a quick-step set in the Bruhat graph. And what this proposition says is that the image, the vertex in the Bruhat graph, which has B as its image, will have this flat as quick-step set. That's what it says. So it's a corollary, if you like. It comes from general theory of matroids that the number of MBC sets that generate a certain flat is computed by this Möbius number. So the Möbius number in the intersection lattice from the bottom to this flat. If you take the absolute value, then that's the number of MBC sets that generate this flat. So the proposition says that all those MBC sets will be mapped to elements that have this flat as quick-step set. So that's this set. So when you intersect this with the image of phi, you must get precisely this number of elements. So maybe the picture makes this clearer on the next slide. But then what we can say, we can take the difference, the number of vertices altogether that have this quick-step set minus the number of vertices that must be in the image of phi. Well, that's some non-negative number, and it counts the elements with this particular quick-step set that are not hit by phi. So this sort of refines what we know about this phi. And here's an example. These are the two posets that you saw before. Here you see the Bruhat interval, and the labels are the quick-step sets. Here you see the quick-step poset, which is isomorphic to the intersection lattice. And you can compute the Möbius numbers in this intersection lattice. I haven't done it, but let's look at a simple example. Let's take the flat C, for example. The Möbius value of the Möbius function from the bottom to C is -1, so the absolute value is 1. On the other hand, over to the left, you have two elements labeled by the set C. And 2 minus this value 1 is 1. So that's the excess of this flat. And if you do another computation at the top, you see that the value of the absolute value of the Möbius function is 4. But you have 5 sets labeled A, B, C, D, E, so the excess is 5 minus 4, which is 1 again. And all the other excesses are actually 0, you can check. So this means that if this is your Bruhat interval, regardless of which element gave you this poset structure, then the map phi will miss 2 elements. One of them will be one of these two, which is labeled C, and the other will be one of these 5, which are labeled A, B, C, D, E. And all the other vertices will automatically be hit by phi. This you can actually connect to a result of Sjöstrand, the one that I mentioned earlier in the beginning. You might ask yourself, okay, so this, if I start with isomorphic Bruhat intervals, then I get isomorphic intersection lattices. But what about the other direction? Well, unfortunately not. So, for example, you have two permutations, 4231 and 3421. They have isomorphic intersection lattices, but one of these permutations corresponds to a smooth Schubert variety and the other does not. So in particular, the Bruhat intervals cannot be isomorphic. And this also shows that smoothness or even rational smoothness of the variety is not an invariant of the matroid, of the intersection lattice, of the arrangement. However, if you use this result by Sjöstrand, you can see that it is an invariant of the matroid if you decorate it with this information about the excess number. So if you reformulate Sjöstrand's theorem, it states that this variety is rationally smooth if and only if the arrangement is free, or I've even written inductively free because that's a technical strengthening of freeness. But the good thing about it is that one knows that it only depends on the matroid. That's still open for general freeness. But inductively free and has this excess 0 for all flats. So this is a property which depends only on the matroid and the excess. And of course, you can ask which other properties of the variety that you can detect using, well, using the arrangement, or maybe the arrangement together with this excess. And one final slide. What we have done here is about finite Coxeter groups all the time, finite reflection groups. And we showed, or at least claimed, that the quick-step poset is isomorphic to, this should state the intersection lattice of this arrangement. In particular, this is a geometric lattice. It's a very nice property. So you can ask, if you start with some other graph and some other starting vertex and insert your favorite poset property, which graphs satisfy it? And one particular instance I'm interested in is if you start with an infinite Coxeter group, then what happens? This proof, which I didn't show you, that the quick-step poset is isomorphic to the intersection lattice of this arrangement, depends very heavily on the finiteness. All kinds of properties that we only have for finite Coxeter groups are being used. So I have no idea what happens if W is infinite. Maybe it's still a geometric lattice, and maybe if it's not, it might still be a nice poset, maybe some nice connections to the Bruhat order. That would be nice to know. Okay, that's it. Back to you, Sarah.
Well, thank you for such a nice talk, Axel. Let's all applaud or reaction, whatever you can do. If you unshare your screen, you'll be able to see everybody's smiling faces. So thank you. Put our little happy claps.
So we have a first question from Martin Ruby, asking if every lattice occurs as a quick-step lattice.
I have absolutely no idea, since I've only investigated this in the context of Bruhat graphs, and they are always geometric lattices. So for other graphs, I have no idea whatsoever.
Are there any other questions? Please raise your little Zoom hand or write in the chat. So Vic Reiner has a question. Do you want to pose it yourself, Vic?
Sure, Axel. Oh, great talk, by the way. Does this quick-step map provide any inequalities or relation between the Kazan-Lustig polynomial from 1 up to W and the Kazan-Lustig polynomial of the matroid for the geometric lattice?
That's an interesting question, and I don't know the answer to it. Yeah, I think that's my final answer.
Okay, thanks.
Okay, thank you. Any more questions?
I have my
comments? Hand. Oh yeah, Sarah, there. Now I see your hand. Okay, I had my chat in front of your face. Okay.
So I was wondering, Axel, have you looked at the quotients in Bruhat order? So Sn mod some parabolic subgroup. Do you get something similar for the quickset poset going on there?
As I said, I've only looked at this for these honest Bruhat graphs. This was the reason I studied it. But I'm not sure.
Bruhat graphs because you just work in some G mod P parabolic. instead of G mod B. So you still
Yeah.
have geometry there.
Pardon, your sound got muffled. Do you still have what?
You still have geometry there because you can work in G mod P.
Yeah, sure. But I'm not sure about the graph, whether it's such a nice thing. I mean, it loses a lot of the sort of the connectedness of the ordinary Bruhat graph. And now, I haven't checked it, but I would be surprised if you could use it for the same kind of purpose. I don't think so, but I don't know for sure.
Okay, now I have to see if anyone else raises their physical hand, their Zoom hand, or writing in the chat. Is there no one else who wants to ask Axel some questions after this great talk? Then I suggest we applaud him again.